Good morning, Algebra 2 students. This is a recording that I'm making for my Algebra 2 class because your whole group, Class Connect, is scheduled on Mondays, and this Monday is going to be Labor Day, so you're going to miss your Class Connect, and I wanted to make sure that you did get some information, specifically reviewing Unit 2. So I'm going to go through this deck. In the email that I'm sending to you, I'm also going to give you the link to the whiteboard deck. So if you would like to get the information from the deck, you can also have the PowerPoint. So I'm just going to skip the do now since this is just a recording, and I'm going to jump right to some announcements. So on Monday, we are out of school. Woo-hoo, hallelujah. It's Labor Day. Tuesday, we have our 2.09 unit test, and regular students do also have part 2. So you have part 1 and you also have part 2. Part 2 is your first teacher graded assignment for this semester. You do have 2 of those. You'll have one in Unit 2, which is the unit that we're in, and you'll also have another TGA in Unit 6. I will do a separate video if you're needing a little extra help with that part 2 of the 2.09 unit test. I'll do a separate video for that. Wednesday, we're moving right into Unit 3, 3.02. It's an optional bonus for regular. Thursday, 3.03 with a quiz, and then Friday, 3.05. So we skip 3.04. Remember, when you're taking your quizzes and your tests and doing your TGAs, you can use your notes, you can use your whiteboard decks that you've saved, and all that good information. All right, this is my slide where I'm just giving you the information that comes from the Alabama Course of Study. So I'm going to jump right in with the rules. I thought that I would make several slides just going over the basic rules that we have learned in Unit 2. So when we're dealing with a radical, so over here, if you'll take a quick look at the remember that when remember that a radical is not always a square root. Okay, your brain, if you're not careful, your brain is going to default to square roots just because we've had more experience with square roots. So it says if a radical doesn't have an index. So let's go over here and talk about some vocabulary words. So if there's a little number written in the top left-hand corner above your radical symbol, that is your index. You could be doing the cube root, fourth root, fifth root. And remember, if it's a square root, there will not be an index written. So if a radical doesn't have an index, remember that's an understood 2. So on this particular example, it's saying what times itself 2 times is 81, and you're going to say 9. And then what times itself 2 times is 49, and you're going to say 7. If there is an index greater than 2, it will be written in the index spot, and then we have the radical symbol, and whatever is underneath is considered the radicand. Sometimes it's a variable, so it will have a base and an exponent. So I'm going to click through. I have several little reminder rules, and then I have some examples to talk about. Perfect squares and perfect cubes can be found using your calculator if you need to. And so I do have a list of perfect squares, 1 through 144, and then I made a shorter list of perfect cubes just because we don't have those memorized. If you are trying to find a square root of a number and you're not sure whether it's a perfect square or not, and you're working on your TI-84, you're going to hit the blue second button, and then you're going to hit the X squared. That's going to bring up the square root key, and then you can put in any number that you want. Remember, if you're not sure whether it's a perfect square, and you take the square root of that number with your calculator and you get a decimal that never ends or repeats, that proves that that number is not a perfect square. We haven't talked about this a lot, so I wanted to make a screenshot. If you were doing perfect cubes, if you wanted to take the cube root of something on your calculator, you're going to have to go to the math key. The math key is right below the green alpha key. Once that pops up, you have several choices here, but number 4 is actually the cube root. And then number 5 would be anything else, fourth root, fifth root, sixth root, and so on. So I wanted to show you that with your calculators. When you're taking the radicals of variables, you cannot use your calculator. I've seen students do this for years. Oh, I'm going to take the cube root of x to the 15th on my calculator. You cannot do that. So you have to know a separate rule for variables. So it says variables that are perfect squares have exponents that are divisible by 2. For example, x to the 2nd, x to the 4th, x to the 6th, x to the 8th, x to the 10th. You could also say their exponents are even. That means the same exact thing as divisible by 2. Variables that are perfect cubes have exponents that are divisible by 3. X to the 3rd, x to the 6th, x to the 9th, x to the 12th, x to the 15th. So that's how you're going to tell whether a variable is a perfect square or if it's a perfect cube. And then if it's a perfect fourth, I didn't list these, but the exponents would be divisible by 4. If a variable is a perfect fifth, then the exponent would be divisible by 5, and so forth. When you're adding and subtracting radicals, you must have like terms. So remember, like terms are the same exact radical with the same exact number underneath. So a square root of 5 and a square root of 5 would be like terms. You would combine only the numbers out in front, and you would keep that like radical. These two square roots of 7s are like terms, and again, you would combine the -5 and the -2, and you would keep that like term, which is the square root of 7. We can't subtract the square root of 7 from the square root of 5 because those are considered unlike terms, and then we would leave it there. That's our rule when we are adding and subtracting. It could be cube roots also. It would have to be the same number under the cube root to be like terms. When we're multiplying, okay, different rule when we're multiplying. We do not have to have like terms when we're multiplying. The steps for multiplying is we multiply outside number times outside number. We multiply inside number times inside number, and then we simplify. So in this example, 4 and 5 would be my outside numbers. 4 times 5 would be 20. 20 stays outside. Square root of 2 times square root of 8, those would be my inside numbers. That's going to give me square root of 16. And then I would simplify. So I'm going to take a look at what's underneath my square root. I'm going to ask myself, is it a perfect square? And it is. So it's going to simplify to be 4. So this is 20 times 4. There's an understood multiplication going on between the 20 and the square root of 16. And then that would simplify out to be 80. So again, when you are multiplying, you do not have to have like terms. That rule is for adding and subtracting. So outside times outside, inside times inside, simplify. When we have exponents that are fractions, okay, a rational number, if you ever hear the word rational number, that's just a fancy term for fraction. So anytime we have a variable, we'll write this a little bit bigger, or a number that's raised to a rational exponent, or an exponent that is a fraction. So I love this analogy of the tree because the roots are always on the bottom. So the bottom of the fraction is the root, okay? A root is another name for index. So that's kind of how I always remember roots are on the bottom of the tree. So the root or the index is on the bottom of the fraction, and then the power is on the top. The power is on the top. And then we could rewrite this with a radical symbol. And then remember, your root is on the bottom. That's the same as your index. And then your base b would go underneath your radical to your power of m. We'll look at a few examples. So it's power over root. Power over root when your exponent is a fraction. I put let's review imaginary numbers. So I don't know how, what your experience is with imaginary numbers as far as Algebra 1. I know that when we solve quadratic equations, we usually have to get into imaginary numbers because we might be taking the square root of a negative number, and that's where imaginary numbers come from. Imaginary numbers come from when you're taking the square root of a negative number. So we had to have a set of imaginary numbers. Where are imaginary numbers used? They're used a lot in electricity. And again, we talked about this the other day. Are we always going to use in our everyday life, everything that we learn in our math classes? Absolutely not. But there's a lot of things that we use that other people make for us or other people develop for us, whether it be software, whether it be electricity. So we have to be thankful for the math, even if it's not something that we use, or we should be thankful, or I'm thankful. I'm not telling you you have to be thankful. But imaginary numbers are used a lot in electricity, in electrical circuits. So when we decided we had to take the square root of a negative number, so let's talk about this for just a second. So if I were trying to take the square root of negative 25, it's not going to be 5, because 5 times itself 2 times is not going to give me negative 25. And the square root of negative 25 can't be negative 5, because negative 5 times itself 2 times is also not negative 25. So do y'all understand that you can't take the square root of a negative number? So a new set of numbers were developed called imaginary numbers because we needed a value for the square root of a negative number. So basically, to me, there are really 2. These are the main rules. And then these other 2 are just kind of developed off of the 2 main rules. So number 1 is that the letter I in the set of imaginary numbers stands for the square root of negative 1. And then I squared, I to the second power in the set of imaginary numbers stands for the number just negative 1. And if we can get over the fact that these numbers are imaginary and just build our math on these 2 concepts, these 2 rules, I is always equal to the square root of negative 1. I squared is always equal to just negative 1. And then I like to go ahead and talk about if you have an I to an even power, it's always going to simplify to be a positive 1 or a negative 1. And again, I'll show you this in some examples. And then if you have an I raised to an odd power, that's always going to simplify into either a positive I or a negative I. But really, the set of imaginary numbers can really just be based on these 2 facts. I is always equal to the square root of negative 1, and I squared is equal to negative 1. All right, those were what I pulled out to be the most important parts of Unit 2. And then I have 11 examples that I'm going to work through. There are 12 problems on your Unit 2 review, and these are not the exact problems that are on your unit review, but I did look at the 12 problems, and I tried to come up with something that was similar to the problems that are on your Unit 2 review. But again, these are not the exact problems, but they should be useful and for you to look at these examples and go back and do your unit review, or even if you've already done the unit review, go on and do your unit test. All right, so we are simplifying here. 54 is setting underneath the square root. I'm going to go ahead and jot down my perfect squares. 1's a perfect square. 2 times 2 is 4. 3 times 3 is 9. 4 times 4, 5 times 5, 6 times 6, 7 times 7, 8 times 8, 9 times 9, 10 times 10, 11 times 11, and 12 times 12. All right, 54 is not in this list. 54 lies between 49 and 64. So I'm looking for the largest perfect square that will divide into 54. 49 will not divide into 54. You can use your calculator if you're not sure. 36 will not. 25 will not. 16 will not, but 9 will. 9 times 6 is 54. And then remember, since there's not an index, my index is an understood 2. So then I'm going to look at my m to the 4th. And if 4 is divisible by 2, then it's a perfect square. So I'm gonna just bring my variables down, and then I'll do this all in the next step. 5 is not going to be divisible by 2. So n to the 5th is not going to be a perfect square. That means I'm going to have an n left under my radical. I'm just going to do this in one step. Okay, so what I'm going to do is I'm going to underline everything that's a perfect square. So 9 is a perfect square, and m to the 4th is a perfect square because its exponent is divisible by 2. So I'm going to take the square root of 9. That means 3 is going to come out. There's already another 3 outside, so those 3's are going to get multiplied together. I'm going to skip the 6 because it's not a perfect square. I'm going to go to m to the 4th. My understood index is 2, so I'm going to divide the index into the exponent. That 2 is going to go into the 4 2 times. So m to the 2nd is going to come out. Since m to the 4th was a perfect square, I'm going to mark it out. And then I'm going to divide n into 5. 2 into 5. 2 is going to divide into 5 2 times. So I'm going to bring out an n to the second, and then 1 is going to be left over. So I'm going to be left with an n to the 1 under my square root. So let's see what I'm left with. I'm left with a 6, and I'm also left with an n to the understood 1. And you don't have to write that 1. And then I'm going to multiply the 3 times the 3, and that's going to leave me with 9 m to the second, n to the second on the outside of my square root, and then 6n on the inside. A lot going on there. Lots of little rules. All right, number 2 is an example of adding and subtracting. And we do have to have like terms when we're adding and subtracting. And I see these square roots of 2's. They're simplified, but I also see the square root of 18. The square root of 18 is not simplified. It's not a perfect square, but 9 will divide into it. So I'm going to rewrite 18 as 9 times 2. And then I'm going to bring down these other square roots. There is an understood minus 1 in front of that square root of 2. And then I'm going to bring down the 3 square root of 2. I'm going to take the square root of the 9. 3 is going to come out. I'm going to do 3 times negative 3. That's going to give me negative 9 square root of 2. Bring down the minus 1 square root of 2. And bring down the plus 3 square root of 2. And I'm not always going to have 3 like terms. That just happens in this problem that these are all square roots of 2. So I can combine them. And a negative 9 and a negative 1 is a negative 10. And then a negative 10 and a positive 3 is a negative 7. And then I bring over my like term. So in this example, I did have to simplify the square root of 18 before I started to combine like terms. In number 3, we're multiplying. So remember, we don't have to have like terms when we multiply. We're going to do outside number times outside number. There's an understood 1 in front of that square root of 12. So I'm going to do negative 2 times positive 1. That's going to give me negative 2. I'm going to do inside number times inside number. That's going to give me square root of 60. 60 is not a perfect square. It falls between 49 and 64. So I'm going to check to see if 49 will go into it. It will not. 36, it will not. 25, it will not. But I do think 16 goes into 60. Let me check that out. Nope. I think it's 4. 4 times 15. So I had to go all the way up here to 4 to find a perfect square that would go into 60. So 60 is going to break down into 16, not 16. I have 16 on my brain. 4 times 15. 4 times 15. I'm going to take the square root of the 4. 2 is going to come out. And so that leaves me with 2 times the negative 2 that's already out there. 15 stays under the square root. 2 times negative 2 is negative 4. And then 15 is simplified. There's no other factors, nothing that will divide into 15 that are perfect squares, and 15 is not a perfect square. So that would be my answer for number 3. Number 4, we're just simplifying here. We're not adding, subtracting, we're not multiplying. We've got a 72 sitting underneath our square root. Let me jot down those numbers again. 4, 9, 16, 25, 36, 49, 64. I'll stop there. I'll go one more to show you that 72 is not in my list. 72 lies between 64 and 81. So I'm going to check to see if 64 will go into 72. Remember, I always start on the big end because this makes my problem shorter if I find the largest number that will go into 72 that's a perfect square. 64 will not go into 72. 49 will not go into 72, but 36 will. And again, if you don't know that, then you're doing 72 divided by 64 on your calculator. 72 divided by 49. 72 divided by 36. So 36 times 2 is going to give me that 72. I'm going to take the square root of 36, which is 6. 6 is going to come out. 5 is already on the outside, so those numbers are going to get multiplied together. And the 2 is going to stay under the square root, and I'm going to end up with 30 square root of 2. All right, number 5. This is where I talk to myself a lot when I'm doing math, and I tell myself right away, hey, self, this is not a square root. Because we do so many square roots, our brain likes to default to a square root. So I'm going to go, this is a cube root, this is a cube root, this is a cube root. So I'm thinking about perfect cubes. I'm thinking about 1. 1 times 1 times 1 is 1. 2 times 2 times 2 is 8. 3 times 3 times 3 is 27. 4 times 4 times 4 is 64. 5 times 5 times 5 is 125. So I'm thinking about perfect cubes. So you've got to force yourself not to be thinking about perfect squares. They're over here. Here are your perfect squares. Here are your perfect cubes. All right, so I'm looking at 64, okay? It's under a cube root. Is it a perfect cube? Yes, it is. Okay, it's also a perfect square, so that's why your brain's going to go, oh, the cube root of 64 is 8 because 8 times 8 is 64. No, the square root of 64 is 8. This is asking you for the cube root, okay? So let's see if we can do this one in one step. All right, I probably need a little bit more room here. Let me give myself a little bit more room because I'm going to have some things that are going to go on the outside. All right, let's start with a 64. And also remember to put your 3 on your radical because if you don't, you're going to leave the 3 off and it's going to be a square root. All right, 64 is a perfect cube. The cube root of 64 is 4 because 4 times 4 times 4 is 64. So 4 is going to come out. And then let's look at x to the 12th. Is it a perfect cube? Well, remember a variable is going to be a perfect cube if the exponent will divide into, if the index, this is the index, if the index will divide into the exponent with nothing left over. So 3 does divide into 12. So you're going to go 3 divides into 12 4 times. So that means x to the 4th is going to come out. And then we're going to mark x to the 12th completely out because the 3 would divide into the 12. So that means you won't have any x's underneath your radical. All right, let's go to the next variable. Will 3 divide into 15 with nothing left over? Yes, 3 divides into 15 5 times. So that means I'm going to bring out y to the 5th. And nothing is left over, so I'm going to just mark out that y to the 15th. Now, will 3 divide into 11 with nothing being left over? 3 is not going to go evenly into 11. Something's going to be left over, so that means I'm going to have a z. So let's go ahead and divide. 3 divides into 11 3 times. So that means I'm going to bring out z to the 3rd. And then once 3 goes into 11 3 times, that's 9. And 11 minus 9 is 2. So I'm going to have z to the 2nd left over in my radical. That just means z to the 11th was not a perfect cube. And I'm going to go ahead and I was always taught to put a little line through my z so my z doesn't turn into something that looks like a 2. All right, number 6, this is the square root of a negative number. We cannot take the square root of a negative number. That means this is going to end up being an imaginary number. So what my algebra teacher always taught me to do is as soon as I realized I had a negative underneath my square root, she said you can think of it like this, like it's negative 1 times positive 50. And we know that the square root of negative 1 is the imaginary letter I. So I'm going to start by taking I out. So I'm going to take the square root of the negative 1 out as the imaginary unit I. And then I'm going to think about 50. I'm going to think about, is 50 a perfect square? So think about my perfect square list. 50 falls between 49 and 64. It's not a perfect square. So I am going to start to find the largest perfect square that will divide into 50. And that is going to be, can't write with an eraser, can I? So will 49 go into 50? No. Will 36 go into 50? No. Will 25 go into 50? Yes, it will, 2 times. So I'm going to rewrite 50 as 25 times 2. I'm going to take the square root of 25, which is 5. 5 is going to come out. it's going to get multiplied times my I, and we just push those together, and then we have square root of 2. 5I square root of 2. And I know I'm going to end up with an I in my answer because of the original problem having that negative under the square root. Imaginary numbers come from negatives underneath square roots. When we're simplifying an I to an even power, I had this on your rule sheet. So if we're simplifying an I to an even power, we know the answer is either going to be positive or negative 1. So that's a little rule. And so example 7 is an I to an even power. So the first thing that I would do is I would rewrite I squared, or I to the 72nd power, using an I squared. So how do I do that? Well, I can just rewrite this. I can't change the value. But remember our rule, when we have a power to a power, we multiply those together. So I'm going to figure out what power multiplies times 2 that gives me 72, because I can't change my problem, but I can change the way it looks. So 2 times, I was about to say 31, and that's not right, 36. So you could do 72 divided by 2. That's kind of what I did in my head. 72 divided by 2, because this 2 times this number has to give me this 72. A power to a power, we always multiply those. Okay, why is this helpful? Because I can start to simplify if I have an I squared in my problem. So I squared, remember the rule that I squared is always equal to negative 1. I'll write it right here. In the set of imaginary numbers, I squared is always equal to negative 1. So I can substitute a negative 1 in place of my I squared. That's helpful because now the I is gone. And then I just need to raise negative 1 to 36. So I know 36 is a really big number, but remember this rule. When your negative 1 is raised to an even power, okay, that means you're multiplying negative 1 times itself an even number of times. That's going to give you a positive 1. If your negative number is raised to an odd power, that's going to give you a negative number. So that's why I to the even could either produce a positive 1 or a negative 1. It depends on what this exponent ends up being. So that's going to be a positive 1. Just to show you, let's see if I can make one up really quick. If I do I to the 10th, I would rewrite that as I squared, and 10 divided by 2 is 5. So this would be 5. So I squared to the 5th. 2 times 5 would give me 10. I haven't changed the value of the problem. In the place of the I squared, I put in negative 1. It's being raised to 5. 5 is odd. Anytime we raise a negative number to an odd power, it produces a negative number. So negative 1 times itself 5 times is a negative 1. So just showing you how when your original exponent is even, it could result into a positive 1, or it could result into a negative 1. Just depends on the math. Number 8, we have I to the 19th. We want to simplify that. So on my rules page, I said if you ever have an I raised to an odd number, your answer will either be a positive or a negative I. So let me show you how you're going to do this one. To me, I to the odds are a little bit harder. So the first thing that you're going to do is you're going to subtract 1 every single time. No matter what your odd exponent is, you're going to subtract 1, and you're going to rewrite it as I to the 18th, because 19 minus 1 is 18, times I. So if it were I to the, 7th, you would subtract 1, and you would rewrite it as I to the 6th times I. You're not changing the value. What you're doing here is you're getting an I to the largest even exponent that you can get it. Then you're going to take that I to the 18th, and you're going to rewrite it as an I squared. So you're going to do 18 divided by 2 is 9. So I squared to the 9th is the same thing as I to the 18th. And then you still got that times I. Your I squared is going to turn into a negative 1. You're going to raise that to the 9th power, and you're going to multiply that times I. If a negative 1 is